Dear students, in this lecture, we will discuss about binary vapor cycle. So, as we know that the Rankine cycle is used for the thermal power plants in which we use the steam cycle. But because of the metallurgical conditions, we also use binary vapor cycle in which two separate cycles are used, and that we will discuss here in this lecture. The main aim of steam turbine designer is to achieve the highest thermal efficiency possible for the plant. This is the objective. Now, we know that thermal efficiency of Rankine cycle can be increased. Number one, by increasing the average temperature at which heat is added. Number two, decreasing the average temperature at which heat is rejected by the cycle. But by the metallurgical problems of the boiler and the steam turbine limit the maximum temperature of the cycle. A metal can withstand a higher temperature but at a lower pressure. At the present state of technology, this maximum temperature limit is 650 degrees centigrade. We cannot go beyond that limit of the temperature for any cycle. Now, the cooling medium in the condenser is a limit to the minimum temperature of the cycle. This temperature is about 25 degrees centigrade of natural water. Now, if the steam is used as the working fluid in Rankine cycle, over the ever temperature range means maximum temperature is 650 degrees centigrade and minimum temperature is 25 degrees centigrade, then there are some difficulties which arise. Number one, the critical temperature of water, which is 374 degrees centigrade. And to obtain a maximum temperature of 650 degrees centigrade, the steam has to be superheated, and this is only possible at very high pressure. It means you have to increase the temperature of the steam, then definitely its pressure will also be increased. The metallurgical problem which arise do not permit high pressure. The metal can withstand high temperature, but they cannot withstand high pressure. So the average temperature of the heat addition reduces, and if the temperature of heat addition will reduce, it will reduce the efficiency of the cycle. The high temperature is therefore desirable at high pressure. Number two is the high initial pressure results in excessive moisture in the low pressure stages. When we use this high pressure steam in the steam turbine, the high initial pressure which will result in excessive moisture in the low pressure stages. Also, in point 3, as the pressure increases, the latent heat of vaporization decreases. The rising pressure, the latent heat added in the cycle or in the boiler also decreases. Water also having some disadvantage at the minimum temperature of the cycle. The condenser operates at vacuum because the saturation pressure corresponding to 25 degrees centigrade is only 0.03 bar, which is much lower than atmospheric pressure. It means the compressor condenser which is operating at the saturation pressure corresponding to 25 degrees centigrade, the corresponding pressure is 0.03 bar. So it is much lower than the atmosphere pressure. So it is essential to minimize air leakage in the condenser, because if the condenser pressure is 0.03 bar and the atmospheric pressure is 1 bar, so there are definitely chances of air leaking into the condenser. It also desirable that back pressure is somewhat above the atmospheric pressure. It means if the back pressure is not the above of the atmospheric pressure, then definitely there will be the problem in the rejection of the steam also. So we observe therefore that all the requirements for an ideal working fluid are not met by water or any single working fluid. So two working fluids are therefore used in the cycle so that most of the requirements are fulfilled. Such a cycle is called as binary vapor cycle. In this, mercury and steam are commonly used as working fluids. The following are the advantages of mercury as binary vapor cycle. So if we are going to use the mercury as the binary vapor cycle, we are having the following advantages. Point one is moderate vapor pressure at high temperature. Means in the case of the steam cycle, if we have to increase the temperature, then definitely it will increase the pressure to a very high pressure. But if we are using the vanadium per cycle or mercury as the working fluid, then it gives only moderate pressure. At temperature around 540 centigrade, the saturation pressure is less than 14 bar. It is very, very small temperature in comparison to the steam or the water. Second is the mercury is very, very stable matter. Liquid mercury has a high density. It is the heavy metal. So it is advantageous in the separation of the liquid from vapor in the boiler and in feeding back to the boiler under hydrostatic head rather than under pumping head. So because there are advantages of the separation of the liquid from the vapor. Another one advantage is feeding the feeding to the boiler. It can be done under only hydrostatic pressure. No additional pump is required. Next point is specific heat of the liquid is only 0.144. So the liquid line is steep, making the cycle closer to the Carnot cycle. Because in the Carnot cycle, we are getting all the lines are the straight lines. The two horizontal lines which indicate the heat addition as constant temperature and two vertical lines indicate the isentropic process. So if the heat addition, the specific heat is only 0.14, very, very small. That will give the steep line, it will increase the efficiency. Specific enthalpy of mercury vapor is low, thus resulting in lower jet velocity in mercury turbines. Because of the specific enthalpy, which is low, will give the lower jet velocity in the mercury turbines too. Thermal efficiency is higher than the Rankine steam cycle. If we are using mercury as the working fluid, then it will increase the efficiency in comparison to the Rankine cycle. But there are some disadvantages. One is the high cost and limited supply. Cost is more and supply is limited. The mercury is toxic in nature. Pervasive, thus tends to break through joints and cracks. It is of the pervasive nature, so there are chances that the mercury and can leak through joints or cracks which exist in the different pipelines. Latent is it is very low, requiring large amount of mercury for the same heat utilization. This is also the not the good point because it will require the large quantity of the mercury because of the low value of latent heat. Whole boiler operates under high temperature and not just the superheater. Whole boiler complete boiler will operate at the high temperature, not only the superheater, but in case of the steam cycle, only the superheater operates at the high temperature. Because mercury doesn't emit the surface, this causes poor heat transfer. This can of course be overcome by chemical treatment. Now we can see here the schematic diagram for this one vapor cycle. So we can see here this is you can say this is the steam boiler. Steam produced by this boiler is passing to the this turbine. This is called as the first cycle is the mercury cycle. This is the mercury cycle. And here this is the mercury boiler. So mercury boiler produces the mercury steam that is passing through this mercury turbine to produce some work by the mercury turbine. Then the exhaust mercury steam will pass through this heat exchanger. This is called as a mercury condenser cum steam generator. So it will pass through this heat exchanger. Then it will release its heat, lose its heat, electric heat. It will change its phase, and at point C, we are getting the mercury in the liquid form. And with the help of the mercury pump, this liquid mercury again supplied to the mercury boiler. This is the boiler, which is the mercury boiler. This is the mercury boiler. Now, so again, this mercury liquid will enter the boiler and it will produce the mercury steam, mercury vapor. In the error cycle, we can see this is the steam turbine, and this portion is called as the mercury boiler cum steam superheater. And here we can see this is the steam condenser for the rejection of the steam from the exhaust turbine, CFP and BFP. This is boiler feed pump. This is the condensate feed pump. So here you can see we are not using any steam boiler here. Now the we can see here the heat, which is the water obtaining from this region, from this area, this is called the mercury condenser cum steam generator. So when the water with the help of the boiler feed pump is passed through this heat exchanger, this is the area, then here you will see what is happening here. When the water will pass through this section, it will be evaporated. It will generate the steam. Then this water will pass through this passage and it will enter here the mercury boiler cum steam superheater. So water steam will come here. The steam will be superheated in this portion. It will superheated here, and the superheated steam then will pass through this pipeline and will enter the steam turbine here. This steam will produce the work by expanding in the steam turbine, producing the work. This is the turbine work, and the exhaust steam from this turbine will pass through this steam condenser, rejecting its heat here, and there will be the phase change from gaseous phase to uh, liquid phase. And with the help of the condensate feed pump and boiler feed pump, it will again pass through this mercury condenser, and the steam produced here will be passed through superheater. So this is the simple working of this mercury vapor fluid, mercury as the working fluid, and the binary vapor cycle. Thank you.